In this video, we're going to start to introduce C code into our operating system. So this is a bit of an interesting challenge for two reasons. The first is that we're currently in 16-bit mode, so we're going to have to use a compiler that's compatible with 16-bit based assembly. And the second challenge is that we don't have access to any general C libraries. So things like standard I/O and these types of libraries, we don't actually have them because they don't exist on our operating system. So what's going to happen is we're going to have to integrate those ourselves by writing the assembly, or in some cases C code, for those actual libraries in order to get their functionality. So I'm going to show you how to get a message to print onto the screen in C using a mixture of C and assembly. So the first thing that we're going to do is we're going to update our make file so that it's able to compile C code. To be able to do this, we're going to use a special C compiler known as OpenWatcom. OpenWatcom is an open source C compiler that is compatible with older versions of assembly in C. So that means that it can compile into 16-bit assembly. So that's primarily what we're looking for from OpenWatcom. I'll show you all the different things that we can do with it as we're continuing on through the process. To install OpenWatcom, you're just going to pick one of these installs from the latest build. In my case, I'm on Linux 64, x86, so I picked this one. I just installed it like any other package. Just run it, and it will install onto your computer. Once you have OpenWatcom installed, what you're going to do is you're going to add a few more things into our make file. I'm going to add in cc16 as a variable, which is going to point towards the 16-bit compiler for Watcom. User bin Watcom bin l wcc. So wcc is the Watcom compiler, and we'll be able to use this in 16-bit mode. Now, there's a few different flags that we would typically provide for this compiler, and that would be the following. We'd have -s, -wx, ms, zl, and zq. And just to walk you through what each of these are, -s is removing Stack Overflow checks and protection because our operating system currently doesn't have that, so there's no need to actually put those in. WZ just sets the warning level to max on this compiler. Just that way we can see all the different warnings that come up to make sure that we're not introducing any bugs into our code. MS sets the memory model of our compiler. So there's a few different memory model sizes that exist. MS is the small memory model, and this is generally going to be used as a default for 16 and 32-bit compilers. So that's why we're using this memory model, is just because it works best and is probably most efficient with our 16-bit assembly. ZL is going to make sure that we don't link in any libraries or references from C, so it's going to remove all of those libraries and references. And then ZQ is just getting the compiler to run quietly, so it suppresses like informational-based messages, which is going to make it just a little bit easier to see the outputs of our compiler. So that gets us set up with our C compiler. The other thing that we need to do is set up a linker. The general linker that we have on our operating system, typically LD for instance, is not going to work with 16-bit assembly. So what we need to do is work with the one that comes with Watcom. So I'm just going to point towards it. It's at Watcom/binl/wlink. And then the final thing is that when we compile assembly that's working with C code, we typically compile it in OBJ format. So I'm just going to give a -f flag, which is for format, and I give it OBJ here. Now, there are a lot of different ways that we can actually build out the code that's associated with our C program. There's going to be a few different C programs that are associated. I'm going to put it inside of my kernel here. And generally, the way that we're actually going to build these out is I'm going to list out the rules one by one, just because it's easier for you to understand each of the individual rules if I show them one by one. Some people will show them like in these general sort of rules that like compile all the C, compile the ASM, link them all together dynamically in like loops. It's a little bit harder to understand exactly what we're doing, so I want to give you sort of more step-by-step, and then we can, make it more efficient later if we want to. So for assembly, we're going to compile everything for the kernel portion here, which is going to be the code that's associated with our kernel. So it's going to have like our C and our assembly. We're going to compile all of the assembly with the ASM flags. Remember that that's the format as OBJ. And we're going to output everything out to builder/kernel. And I'm going to place it at a particular location. We're going to place it in ASM, and then the first file that I have is main.obj. And that's going to result from compiling together the source dir/kernel/main.asm. And that file currently exists here. We've had that for a bit. We're going to change it in this video, but it is currently present in the directory. There's another assembly file that we're going to put together, which is called print, which is going to have code for printing things to the screen. So we're going to call this print.obj, and it's going to be print.asm. Now we're going to have some C files as well. So we're going to have cc16. This is going to have the various C flags that we have available. So C flag 16. The output for this, like the others, is going to be in builder. I'm going to place it in kernel/C. This one is going to be called main.obj, be our main file. And it's going to be located at sourcedir/kernel/main.c. So that's going to be our main file. And then I'm going to do the same thing again, and it's going to be for our other C file, which in this case is not going to be main, it's going to be stdio. And this should be just .o rather than .obj. So I'll just change these two here to be .o rather than, or sorry, actually they should be .obj. We'll do them both as .obj. That way the formatting is consistent between the ASM and the C files. So this one is not going to be main.c, it's going to be stdio.c, like this. So those are all the files that we need to compile, and then we just need to link them together, which we do using our 16-bit linker. It takes in the name of the files that we're looking to link. So builder/kernel.bin is what we're creating. The files that we're linking together are going to be listed in an array like this. So the builder/kernel/asm/main.obj. So we need this file. We need the print file, we need the kernel file, so we're just going to get all of these together. So we have main.obj, we need to get print.obj out of ASM. We're also going to need to get the C files, right? So C/main.obj, and then we also need C/stdio. So those are all the files that we need to link together. And this works basically the exact same way that like a linker would generally work. It takes in all these different files. There's a few syntactical things to make sure that you have. These dashes in front of the brace brackets is very important. And then it requires something called an option map. An option map is basically going to give us all of the different mappings that are associated with our kernel. So it helps to map all the material together. And that file is called kernel.map. It's actually generated from our C compiler. So you'll see that once we actually go through the process of building everything. And then we're just going to point it towards what's called a linker file, which is something else that we're going to create. The linker file is going to define how everything is linked together. It's going to give the structure of our resulting binary. So we've defined all of the rules for building our project. Just one final thing that I'm going to do. I'm going to create a rule called always here. And what it's going to do is it's just going to create the directories for everything that I've defined inside of my kernel. So that being builder is the first thing that I need. I need builder/kernel, kernel ASM, and then kernel/C. So /kernel, just to make sure that all these files are created, because when I run my build process, I typically have it clean out that build directory. So this will just ensure that all those files are placed back where they need to be. So now we have everything in our build directory created. What we need to do now is create, of course, all of the code associated with what I just defined. So first things first, I'm going to make my linker. My linker is just going to define how the binary is produced from the linker file. So we give it a format. So the format is a raw binary. I can provide some different options for it. Typically, I would provide the option quiet just to reduce the amount of noise that comes out of the compiler. And then we want to make sure that no default libraries are put in. Like I said before, we don't have any C libraries, so we want to make sure that those aren't provided. We provide a starting point, which is typically called entry by convention. There's a few different options that we can provide here. Typically, we provide a verbose option, and then we provide an offset and a stack. Remember, this stack address is actually matching the stack address that we were working with inside of our boot.asm file. So we're just making sure that our memory model is set up in a consistent way when we produce this binary so that it's able to run compatible to our disk. That's primarily what we're doing here. Now we're going to set the order of the file, which basically just defines the ordering of everything. So we have our code CL name. Inside of this, there's a segment for entry, which is the entry point of the application. We have a segment for text, which is all of our text instructions. And then we have the data, which follows after the code. This just defines how the structure of the file is going to be set. That's everything that we need for our linker. Now from here, what I'm going to do is I'm going to start by creating my main.c file, which is going to have all of the C code that I want to use. Now what you're going to see here is I'm going to include some libraries like I would usually do in a C program. However, like I said, these libraries don't exist yet. We don't have them, so we actually have to make them. We'll see how we can make them inside of our application. But I'm going to start by defining my entry point, which typically uses cdecl. This is a convention for working with the assembly language that we are using for this. So just for each of our functions, we're typically going to have that cdecl to be able to associate it with assembly. And then typically the entry point is named c__. Now I can provide some arguments to this. I don't need any arguments yet because I am not going to be doing anything with arguments. All I'm going to be doing is I just want to print out the message, hello world from C. Okay, that's all I really want to do for this process here. Now, in order to do this, I have to implement stdint and stdio. And what's interesting is that we actually already know how to print data onto the screen, right? We saw this through BIOS interrupts. So we're going to be able to do this pretty reliably inside of our system. So we'll take a look at each of these in detail. So we'll start with standard IO. So I'm going to create a file named standardio.c. And I'm going to create a file called standardio.h. Now what I'm also going to do is I'm going to create a file called print.asm and a file named print.h. So print.asm and print.h are going to be the low-level part of my print function. Standard IO is going to be a way of interfacing with this lower-level print. So it's like an abstraction of it. So inside of print, what I'm going to do is I'm going to just define the actual function that I'm going to use to print data onto the screen. So I'm going to include standardint.h. Again, this is something that I haven't made yet. We'll make this in a moment, but we're just sort of defining out some of the basics here. So we're going to have a function. It's a cdecl. I'm going to call it x86 video write char tele type. It's going to take in a character C to print and a uint8 underscore t page. Now, if you recall, when we worked inside of assembly, and let me just word wrap this so it's a bit easier to see. When we worked inside of assembly, there was a way of being able to print data onto the screen using a page as well as the data that we wanted to print. So we're going to do exactly that, and we're going to do that in print.asm. This is where we're going to implement this function here. So the way I do that is I've set the bits to 16, of course, because we're in 16 bits still. I'm going to set up a section for text, and we give it a class equal to code, just to specify that this is code that we're working with. I'm going to define a global for x86 video write char tele type. And basically all this is doing is it's exporting this function so that it's accessible to other files. And then I'm going to define the function here, x86 video character tel type. What it's going to do is it's going to push BP on, and then it's going to move BP into SP. This is the general setup of, a function, right? We preserve the base pointer and then move the stack pointer into the base pointer. We are then going to preserve any parameters that we might overwrite when we're going through this. I move into AH the value 0EH. I move into AL BP plus 4. I move into BH BP plus 6, and then I do an interrupt ADH. Now if you, or sorry, not an ADH, a 10H. Now if you remember, I think we have it in main.asm, we had this sort of idea defined, right? Where we have this int 10, right? And you saw here that we had this general setup where we had AH being set to 0EH, or 0x0e in this case. Both of those notations are going to work equivalently. And then we give it the value that we want to print from AL and then where we want to print it in terms of the page in BH. So that's all we're really doing here. This is retrieving the parameter off of the stack. It would be plus 4 from the base pointer. And this is plus 6 because it's the parameter that follows. So this is the character that we're printing, and this is the page number. And then int 10h is going to print it. We're going to pop bx to get it back to the state that it was before we ran this function. we move the BP back into SP, we pop the BP off the stack, and then we return. This will print data onto the screen. So we now have the way of printing data at the low level. Now the next level up is standard io.h. Standard io.h is going to define my different functions for printing data. So I'm going to make one called putc, which will print a single character onto the screen. I'm also going to create one called puts, which is going to print a whole array of characters onto the screen, or a string in this case. I typically like to provide a pragma once for this, just to make sure that all these are only defined once, right? So that's something that I typically put onto my header files in C. Now we can implement these in standard io.c, right? We simply are going to include standard io.h, and we're of course going to need our print, so we are going to include as well print.h. Now the two functions that I have are going to be pretty simple. For putc, all we do is we call the x86 video write char type with the character that we want to print and a page of 0. Now for puts, we just do the same thing, but we do it inside of a loop. So we could just say while star s, put c star s, s++, right? We're just calling this function here in order to print the single character. We could also take this down and place it here, but that would repeat the code. We don't really need to do that. So we're okay with just working this way. So this gives us our way of actually printing onto the screen. Now, one final detail that we need is this standard int that I've been defining. And this is going to give us just some standard types to work with. So this is something that you might be familiar with in C. We have this simple little type def, which just creates some nice little shortcuts for defining integers and similar data types. So generally the way that this works is we have both signed and unsigned versions of our data types. So for instance, we could have, a signed and unsigned character, which we call int8t for the signed one and unsigned int8t for our signed one, or for our unsigned one, right? So you can see here that we're basically just defining different versions of these characters so that I don't have to use like unsigned char since it's a long keyword. We could just use this shorthand instead. This is something that you typically see inside of C, and we do it for all the different sizes. So we would have 16, and in C, 16 would generally be a signed and unsigned short. And then we would have 32, and 32 is typically going to be a long int, like this. And then we would have 64. And 64 is generally going to be a long int. So we would have something that looks like this, long int. And again, really the only reason why we do this is just because like typing long int is a lot of keywords compared to just int64t. Just makes it a bit easier to work with, right? So that gives us all of our stuff that we need for printing. So that's a really good step forward. Now, the final thing that we really need to do here, just sort of taking a look at everything that we have our main.c, which is going to call our puts function. We really just need to get to here from where we end up after our bootloader. So our bootloader, if you remember, loads this main.asm file. We want this main.asm file to jump into our C code. So I'm going to get rid of all of this. I'm going to set the bits to 16. I'm going to set up a section entry class equals code like we had before. I'm going to set up an extern C start and a global for entry. So the entry is just going to clear our interrupts, and it's going to set up the initialization of data. So this is something that we saw when we first started inside of our bootloader. We were setting up a thing to clear the AXSS and setting the SP to 0 and setting up the BP as well. So we're just initializing all these different registers. Once we have those, we can STI, and then we can go ahead and get into our C start. And in order to do that, generally, all we're going to do is we're just going to call C start. Once that's done, I'm just going to CLI and I'm going to halt, just to make sure that we don't progress any further from this. This will halt execution of our application. So this is going to jump into C start, which is going to take us here. This calls puts. Puts is defined in standard.io.c, which loops through the string that was provided and calls x86 write char tell type. This here is defined in print ASM. And I just realized inside of here, I didn't put the underscore here. So just make sure that we have that. Make sure that I've defined that consistently, which I have not. So the underscore should be here, I believe. So that should set us up correctly, right? So we have the underscores all set there. Oh, actually, sorry, that's my mistake. It actually doesn't need the underscore there. The reason for that is because we only have the underscore inside of the assembly code. That's just out of convention. So sorry about that. We don't have those two underscores. Those are actually removed. So with this, we should now have working code if everything is set up correctly. So let's go ahead and give it a try to make it, see what happens. You can see here that it's having trouble opening build kernel main obj. Let's just take a quick look here and see. It looks like, oh, it hasn't created the folders for us. So inside of the make file, it didn't run this always rule. I probably just didn't actually put it in. So let me put it inside of here and we could try that again. It looks like it still didn't create it. I probably have to put it here, or I might have to put it inside of clean. Might make more sense. There we go. Now we're getting it going. So looks like we just have a small error in ASM, print.asm 13 and 14. So let's just get that printed up, fixed up. Print ASM 13 and 14. It looks like it's having some trouble with these actual moves. So if we're taking a look at this, it's moving into AL BP plus 4, into BH. Oh, I forgot the commas. That would be why that's not working. There we go. So let's try this again, see what other errors we might get. You'll see here that we generally get a few different warnings that are for new line characters. It looks like we have an invalid option WZ inside of our compiler. So that's one thing that we're going to have to fix here. So that's just inside of the flags here. I might have had the wrong flag defined here. So it's not WZ, sorry, it's WX. There we go. So that's WX here inside of this flag. So that's just one other thing to fix. And then again, we'll just take a look through here. We have a directive error near main.asm. So again, we'll just take a look at some of this troubleshooting as well. So inside of kernel, we do have main.obj, and stdio.obj. Whenever we have errors like this, we really just want to understand where these errors are happening. So in this case, it's in the make file, line 37. So I'm taking a look at my make file, just over here in line 37. It looks like it's actually an error inside of the linker. So let's take a look at our linker one more time. We'll just look in a bit more detail. And really, there's just two errors here. So it's that this kernel here, ASM stdio.obj, this should be C, because this was one of the C code files. And then the second error here is at the top of the linker, after the name, we actually have to put file just before we list all these different files as a part of the linker syntax. And with that, now when we run make, everything will work. So at this point, we can actually try to run our operating system and see what happens. So to do that, we're going to run our QEMU command, of course. So to do this easier, I actually have this run.sh file, which has the command for me. So this is the command that we're running. In this case, I'm just going to run my run.sh file, and it will run it for me. And you'll see if everything works successfully, that we'll actually get this hello world from C, which is exactly what's printing from the C code that we defined inside of our main.c. And with that, you are now able to work a little bit with C code while integrating also your assembly. So we're able to work between C and assembly to be able to integrate our various different libraries to get things up and running. So with that, you now understand a bit more about how we can work between C and assembly, especially at the operating system level. So thanks so much for watching this video, and I'll see you in the next one.